Welcome back. This is part 4 of chapter 1. Thank you for hanging with me. What we're going to look at now, we're going to take those significant figures that we learned about in the last section, and we're going to use those as we are calculating with measured numbers. And then we're going to talk a little bit about accuracy and precision, and we'll see that in the lab for sure. All right. So when we calculate with measured numbers, we are going to either subtract, multiply, add, or divide. And so in addition and subtraction, your answer cannot be any more digits to the right of the decimal point than the original number with the smallest number of digits to the right of the decimal point. What do I mean? Okay, so we have 102.50 has 2 digits past the decimal place. We're going to add that to 0.231, which has 3 digits after the decimal place. And so when we add those together, we get 102.73, and that's just what our calculator would say. That's what we would write down as a number. This final number, though, can only have this, since this one had 2 decimal places, this one had 3 decimal places, our answer can only have the smallest number. So it's going to have 2 decimal places, so we would have to round that to 102.73. So subtraction is the same thing. It's about the decimal places. I got 2 here, I got 1 here. So my answer can only have 1 because that's the lowest number. So my 123.19, I'm going to have to round to 123.2. Notice if this number is 5 or greater, you're going to round up. If the leftmost digit to be dropped is less than 5, round down. If it's 5 or greater, round up. That's the rule that we're using regardless of whatever rules you have seen in the past. So in multiplication and division, it's a little bit different. You're going to look at total significant figures in the number. So for example, I have 2 significant figures in 1.4, and then I have 4 significant figures in 8.011. So my number can only have 2 significant figures. And in that case, it's only going to be what? 11 with no decimal place. Okay? If I divide, same thing. It's total numbers of significant figures. So I have 4 in the numerator, and I have 5, 1, 2, 3, 4, 5, 5 in the denominator, and so the lower number is 4. So I'll calculate 0.0378252909. That's what my calculator spit out, right? I'm going to have to round that to 4 significant figures. So 1, 2, 3, 4. And that last one I'm going to round up because the next one is a 5. So 0.03783 would be the correct answer. Exact numbers, as we said before, have an infinite number of significant figures, so they do not limit the number of significant figures in a calculated result. Typically, the measurement is what's going to dictate how many of these significant figures you're going to be able to use, because if it's how many of it, that's an exact number. If it's a conversion factor, that's an exact number. So your measurement is usually the one that kind of dictates how many you're going to use. If you calculate using multiple steps, if you round each one, you could come up with what's called a rounding error. So if you notice that you're different from the answers, then that may be what's going on. In general, it's best to retain at least 1 extra digit until the end of a multi-step calculation to minimize rounding error, but you have to remember how many it really had in order to apply it correctly to the calculation. So it's easier for me to show you than to tell you. So this first one, 317.5 plus 0.675, that's addition. okay? And since it's addition, it's going to matter how many decimal places. So I have 1 here and I have 3 here. So it's best when you're doing these, line them up where that decimal place is in line. So I'm going to say 317.5 plus 0.675. And when you're doing it, kind of draw a little line like that. That'll show you 318.175, okay? And so that shows you that you're going to use this many, but you're going to have to round that last one up because the next one was a 7. So your answer would be 318.2. With me? All right, same thing when we're subtracting. You're going to get, and you're going to do it like that till you get the hang of this, okay? So this is going to be 45.725 from the calculator. You've got 2 decimal places and 3 decimal places. So 2 decimal places it is, so 45.73. When we divide, we're going to use the actual significant figures. 13.5 grams divided by 45.18 liters is going to give me 0.2988. All right. In division and multiplication, it's how many. This was the least number of SS. So I have 3 significant figures here and 4 here. So my answer can only have 3. So that's going to be 0.299. Makes sense? And that's grams per liter. Always do your units. So kind of getting the hang of this. Now this one, I'm going to erase this for a second. 6.25 times 1.175, okay, is going to equal 7.343 out of the calculator. You've got 3 significant figures and 4 significant figures, and so you're only going to be able to have 3. So that's going to be 7.34. Notice what your units are. You had centimeters times centimeters, okay? So that's centimeters squared. Remember, you're always going to multiply your units just like you are with the other. In scientific notation, this can be a little tricky. What you usually want to do is get them to the same annotation. So 5.46 times 10 to the second would be like 54.6. No, sorry, my bad. Let's just do what the numbers are. That's another way you can do it. 546 and 4991. Okay, so you add those up and you get 5537. All right, and so when you do those, remember you're doing these to decimal places. So decimal places, you're going to have 5.537 times 10 to the third, I think. Okay, now remember that you're going to have to go back. The reason it's to the third is because you have to go back over this. So when we do these, this one had 3, this one had 4. That's why my final answer is going to have 3. Okay, so when I'm doing this, I'm going to have, because it's decimal places, right? So you got 2 decimal places and you got 3 decimal places. So when you add those together, you get 5537 when it's a real number. When I do it back to the regular, that's going to be 5.537 times 10 to the third, right? And some of y'all might want to say 5.54 times 10 to the third. Which one do you think is right? Depends on how you work it. All right, and it depends on your measurements, but you really should have 3 in my opinion. But the book says 5.537. Go figure. All right. See? Because it converted them both to squared, which is another way to do it. So it, instead of 4.991 times 10 to the third, it did 49.91 times 10 to the second. Added it to 5.46 times 10 to the second. And so when you add those together, it's 55.37 times 10 to the second, or 5.537 times 10 to the third. So that's why I'm saying you could get it. It depends on how you calculate it. So there's a little ambiguity in significant figures. All right, so here's some for you to try for practice. In this one, we have a volume of 9.850 times 10 to the second cubic centimeters. The flask is weighed, and it has 124.6 grams. We fill it with gas, we weigh it again, and it reads 126.5. So 126.5 minus 124.6 is going to give us 1.9. So the 126.5 minus 124.6 equals 1.9 grams. So this is the, let's say, a flask plus the gas, and this is just the flask. And so when you subtract those, it gives you the mass of the gas, okay? And then to determine the density of that, we're going to say 1.9 grams divided by 9.850 times 10 to the second. Make sure that you put that in parentheses when you're doing it in your calculator. And that's going to give you 1.9 times 10 to the minus 3. It was 0.1928 is what we got, but we can only use two significant figures. So 1.9 times 10 to the minus third. Okay? This was times 10 to the minus second. Okay? So we have to do it in the correct format. So here it is, all pretty for you to look at. And then there's your practice one. And this is going to be the same kind of problem. And then there's another practice one using the graduated cylinder like we actually do it in lab. All right. I'm sorry, keep coughing. The last part of this is just about accuracy and precision. Accuracy tells you how close you are to the true value, and precision tells you how close your attempts were to each other. So if you get them all close to the same place, you have good precision, but you didn't get them in the trash can, so they're not accurate. If they're all around the trash can and not in it, that's not accurate or precise. If it's all in the trash can together, it's precise and accurate. So how we use this is typically in looking at data. If we're looking at the true mass, and the true mass is given to you here. So 0.370 is the true mass, okay? Now, in this first one, we got 0.335, 0.331, 0.333, all close together, right? But not really close to 0.370. So they were precise because they were all together, but they were not accurate because they were not close to the true value. Let's look at C for a minute. 0.369, 0.373, 0.371, that's going to average really close to 0.370, right? So they are close to the true value, and they're close to each other, so they are accurate and precise. This one, there's the true value. You had one that was kind of close to it, but the others were all over the place. So this one is neither accurate or precise. And as we said, this one is precise but not accurate because they were close together but not at the true value. All right, so that ends part 4 of chapter 1. Thanks for hanging.